afternoon. Welcome to the Thermography and Air Tightness webinar. We're in week 8 of our SUHO webinar series, so thank you for joining us today. My name is Jessica Allen and I'm an ESD consultant with SUHO. So let's get started. This webinar, as with all of our webinars, are all eligible for a Green Star CPD point, a Sustainable Development CPD point. So if you would like one of our certificates of attendance, please make sure that you interact in the chat, and you can email us at info@suho.com.au after the webinar for your certificate. Okay, so as I said, this webinar is going to be on thermal imaging. We use thermal imaging in our blower door testing audit service. So if you contact us for our blower door test, we will bring along our thermal camera and take some pretty pictures for you. So what is thermal imaging? Thermal imaging cameras translate thermal energy into visible colours and enable us to analyse surroundings. These cameras can be very precise and don't require much heat difference to work. So typically we need about 5 degrees difference indoor-outdoor temperature for the images to be of any use. And we can use these images for a lot of different things. So we use it for thermal performance auditing. Thermal imaging can be used for electrical audits. It can be used in the health system. The police use it in their detective work. And like I said, we use it in our blower door service. So a fun fact, infrared technology or thermal imaging sort of had its origins back in the late 1800s. But the sinking of the Titanic, I found out whilst researching for this presentation, was actually a bit of a incentive for thermal imaging development, because the idea was that the icebergs, so the people who were developing the software wanted to be able to detect icebergs, steamships and other sort of non-visible items in the distance. So that's a bit of I thought that was rather interesting. The first camera was actually invented for the British military to detect enemy aircraft in between World War I and World War II. So when I use a thermal imaging camera, I use it when a house is under positive or negative pressure. So when we exert pressure on a house, the air starts to move around, and if we point a thermal camera at it, we can actually see what it's doing. It's a lot easier to use a thermal imaging camera under negative pressure, because when you're sucking air out of a building, the air is brought in all the gaps and cracks in the building fabric, and you can actually see it on the inside of the house where you're standing. If the house is under positive pressure, you have to be standing outside the house to be able to see the airflow. So the air is being pushed into the house, which means that any air that is in the house is thus being pushed out of the gaps and cracks. So you have to be standing outside the building to be able to point the thermal camera at the source and see what's going on. I don't find that way to be as effective in determining air leakage specifically. You can see a lot of differences in surface temperature, but air leakage is not so easy. If you wanted to do a pressurization test and detect air leakage, you're better off using smoke. So yeah, under depressurization, thermal cameras can be a lot of fun. Okay, so in one of the audits that I do, the things that we're typically looking for are air leakage, of course, missing or damaged insulation, thermal bridging, water ingress, so leaks, and electrical faults. Thankfully, I have not found any electrical faults as yet, and I've only found one instance of a water leak in a bathroom ceiling, but I couldn't find the image to put into my presentation today, but I've got plenty on the other 3 topics. So we'll go through a few images. The next few slides are going to be some images that I've taken myself at various different projects. All of the images on this page were taken at the same house, and I think potentially the next slide as well. This was a particularly bad example, but really good for demonstration purposes. So here we have some fairly significant leaks around windows and around unsealed downlights. So if you've seen one of my presentations before on air tightness testing, you will have already heard me say that air leakage looks like paint splashes. So every single one of these images here, you can see it looks like someone has splashed paint on the wall here. So I've got the thermal image and I've got the actual image right next to it, so you can see exactly what's happening in real life. So we've got some air leakage happening up above this window. We've got some air leakage happening around this unsealed downlight, and there were probably 20 downlights on this level. This window here, this is the bottom of the window, and this is the top of the very same window. So on closer inspection, what we found was that underneath the architrave and above the very top of the architrave, there had been no silicone and no paint, because trades just get a little bit lazy when they think that no one's going to notice, and so they had just simply missed out that step of doing the siliconing and the painting on the top and the bottom of that window frame. This one again is from the same house. Pretty much every single window in this house leaked like this, so it was quite surprising. It's probably the worst one I've seen, and this was actually meant to be a 7.5-star house that was built about 10 years ago. So a lot's happened since then. Energy efficiency has come a long way, but the difference between what was designed and what was rated and then what was built was quite significant in this instance. This one here is an image of a sort of an oldish kind of exhaust fan that doesn't have a damper on it. So you can see the purple here around the edges, indicating some cold air coming through. This one is a wall ceiling join. I don't often see air leaks like this at junctions between walls and ceilings and wall to wall. They're usually pretty well sealed, even if there's cornice or square set joins. They're usually pretty good, but this one had some fairly bad air leakage coming down the wall, and this was a new house as well. This is another example of a wall ceiling join, but this one was an older house. This house was in the hills, and this house was probably 40 years old or so. So it's sort of these sorts of things to be expected. It's possible that this leak here, this junction here, wasn't quite finished on test day, but when I come in to do a blower door test, these sorts of things, there shouldn't still be any work like this to be done. So that leakage was quantified in the test. So yeah, you can see there's some fairly standard sorts of constructions here that are supposed to create an air barrier to protect you from the outdoors. This one in particular, oh hang on, where is it? I thought I had one under a door as well. Maybe I don't have one under a door, but this sort of leakage is quite common under front doors and under garage doors as well, quite bad. In fact, it was quite windy here in Adelaide last night, and I was standing near my front door to turn the lamp on, and my feet were freezing because there was heaps of air coming in underneath my door, which actually does have a seal on it, funnily enough. It's just not making proper contact. So there was still a whole heap of air leaking under my door. The whole floor near my front door was quite cold. The other thing that we find that's not directly related to air tightness, but is very common, is missing insulation bats. So here we have a few examples where in this corner, don't know, maybe they just couldn't get to the corner. Sometimes there are access issues in roof spaces, but that little section over in the corner of the roof is missing a bat completely. This example here, it looks like there's been some disturbance around maybe some of the electrical penetrations, but this insulation bat is not making full contact with the ceiling. So there's just at the corners, perhaps it's pushed up against the rafters and it's just lifted off the ceiling. So it's not as fully effective if the insulation is not completely in contact with the ceiling. This one here is another very, very common thing that we find, in that the downlights, there's two downlights here that you can see, and the insulation bats above each one it looks like they've been completely removed. So the insulation gets laid in the ceiling by one contractor, and then the electrical contractor comes through a few days later and moves the bats out the way in order to do their work, plug their stuff in, wire their stuff, whatever, and then they don't put the insulation bats back, and any normal homeowner won't think to get up into the ceiling to make sure that their insulation is actually being put back. So if you've not only have you got leaking downlights like this one, potentially above that downlight, providing that they have fire rated caps above them, of course. You've got leaking downlights and you've got missing insulation. So those sorts of things, when we do energy assessments, we do a ceiling insulation loss calculation if you have downlights that don't have fire rated caps on them. We calculate the missing insulation around each downlight. We count the downlights, and then we have a certain area around each downlight that we have to subtract from the R value. But this, even if you had a downlight that didn't have a fire rated cap over it, the amount of insulation here that is missing above that downlight far exceeds what we're going to calculate. That's like an entire bat has been, or half a bat has been removed to give clearance around that downlight. So heat and cool, particularly, heat in particular, just take the least path of resistance straight up through the ceiling and out into the roof and up and away. So making sure that you have a continuous insulation barrier and making sure that your insulation has been relayed properly after any electrical work is one hot tip. This one here is a wall, an incomplete wall, so that you can see there's some little insulation poking through just over here. There was a bat in the wall missing completely. So I think there might have been potentially an electrical box on the other side or some such thing. But instead of cutting around the electrical box, the whole bat has just been removed. So these builders were actually instructed to take off that plasterboard. Luckily it hadn't been painted and we were in there early enough. The builders were instructed to take off the plasterboard and reapply the insulation. A little image here. So here we've got some visible insulation, making quite good contact with the studs, but you can see on the thermal image here that there's actually some gaps, particularly around the corner junction. What we often find is that there is no insulation in that corner junction. Now sometimes access can be a little bit tricky, but again, least path of resistance. If you've got a non-continuous insulation barrier, you're going to get heat transfer through those gaps. Hang on, what did I miss? There was another one I want to show you. Where's this one? Thermal bridging. Thermal bridging is another issue related to thermal comfort. So this image here is a timber frame. You can see the studs through the plasterboard. So you've got some reasonable thermal bridging issues here, but this is a steel frame, and if you've seen one of my presentations before, you will have seen this image. The steel frames really light up quite brightly. Unless there's a thermal break in there, you're getting heat and cold transfer directly from outside into your house. So when I talk about air tightness and air leaking out through gaps and cracks and affecting your comfort, that is certainly one factor that is going to impact your comfort and your energy bills. Thermal bridging is another one that's going to impact how comfortable you are. And here we have an aluminium window frame as well that's glowing. Well, it's not glowing, it's purple because it's cold, opposite of glowing. But you can see there's a very stark difference in color tone. So there's just a few examples from projects that I have found in my travels. Another short, sharp and shiny presentation from me today, just to illustrate a few of the more obvious defects that we find time and time again. So if any of these ring true for you, you're not alone. And yeah, thanks for watching. One thing, we did a Sustainability Expo last year, and we were having a bit of fun with the thermal camera. People were walking past and we were taking photos of their faces. And one funny thing that we found, just for a little bit of a fun fact for a Wednesday, is that all of the men had warm noses and all of the women had cold noses. We had a bit of a giggle, and I thought I would put some funny pictures up just because I can. So yes, that's all I have today. Some really, really good examples of the defects that we find. Tomorrow we have navigating ESD and town planning, a walk through our 10-star house, some more information on our predictive software Hubble, and some information on use of music modelling in town planning. So I hope that you can join us at one of those webinars. I hope that the pictures I showed you today weren't too shocking, and that you learned something, and I will see you next week. Bye. Oh, wait a minute. No, I won't. Before I go, well, I'll answer the questions. Sorry, nearly cut you all off. Oh, Timo, could you hear me? Timo, Shiva. Hello, Steve. Good afternoon. Angie, hello. Do you usually require active heating or cooling, or do the buildings tend to provide the 5-degree temp difference naturally? Steve, in winter, thermal imaging is quite useful. It's quite interesting. It's more, it's easier to do because the indoor-outdoor temperature is usually bigger. In summer, it's more tricky. You usually have only got a couple of degrees difference between inside and outside. So in that instance, we would recommend that the clients put on their air conditioning before we get there so that the internal surfaces are nice and cool, and that way we can get that temperature difference to show up on the camera. Repeating, when depressurizing, thermal imaging from inside the building is better and vice versa. So yes, when you're depressurizing, all of the air that all the leaks are having air come into the building, so you'll be able to visually see them on a thermal camera and feel them with your hand. When you're pressurizing, the air's going the opposite direction, so thermal imaging won't be very useful to you unless you're on the other side of the building, at which point, like when you're on the outside, you're going to have other issues that are impacting, like the sunshine on the building. There's a lot more outside influences that are going to impact the images that you're seeing, and I have actually tried to do this a few times, but it doesn't work as well if you're looking for air leakage. If you're looking for air leakage and you want to stand outside the building, I would recommend using smoke instead. Inside the building, thermal imaging is, you can use smoke inside as well, but thermal imaging is really fun, and it's kind of a fun exercise, and it's a bit exciting to do. There we go. Yeah, so tomorrow, like I said, the walk through the 10-star house is the 10-star house is now nearly finished. It's very exciting times for SUHO. This has been a long time coming, this project, so we're very excited and very proud of it. We did the air tightness test on it last week. The results were excellent. You can go back and the webinar that I did last week will announces the results. We didn't do any thermography on that day. It wasn't required because we knew the results were going to be, or really only after the air tightness result. But we did do some thermal imaging on it the first test we did. And again, we didn't find very much because the results didn't differ from the first test to the second test at all. So, yeah. Okay. Well, I think that's it for today. And thank you again for joining us. And I hope you enjoy the rest of your afternoon. Bye.